All right. So, what we talked about last time was the following stuff up here. Essentially, it was not specifically that, but it was solving systems through state points. So, remember, we talked about this in particular. It was something sort of like this. It was this state 1 to state 2 question, where at state 1 we were given some things, state 2 we were given some things, and we were told the pressure volume relationship in between using the polytropic process, right? And so we were given, some internal energy change, we were given some volumes, some pressures, and we were told to find everything else, right? The heat transfer, the work. And so that's kind of how this question turned out. Remember what we did is this delta KE plus delta PE plus delta U equals Q minus W. And then it transformed when we know these two didn't actually exist because we were neglected. And then we moved down and down and down until we found a heat transfer. So, next part is that there's other systems, like for example, before we move on, I do want to say there are other systems like this where this it slightly changes. So, this first question right here, we're not going to do it, but I'm going to tell you it's basically a difference, right? Essentially, the difference between this one and the previous one is that there is some work happening in two different ways. At least I believe so. I think that's what they, because they said that this resistor, I think, is doing something. Let me see. Friction. Da, 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 da. Yeah. So essentially, this one is done the same way, except that this time we're having work done on the piston by atmospheric pressure pushing down. So it uses a different equation that honestly you won't see in any other question in this class. But just to tell you that there are other ways that this question can be asked, where you subs things out and you find other things, right? So let me move down to where we are starting today, because the rest of the stuff is things that you probably won't see ever again. But that first question that we did, you will see. So this is a question right here, or this is the next section. So it's 2.6. We are energy analysis of cycles. So let's get basically what a cycle is. So a thermodynamic cycle is a sequence of processes that begins and ends at the same state. So more or less is that the very beginning of it starts at somewhere, right? And then it does something, so it goes from like state 1 to 2 to 3 to 4, and then 4 ends up back at 1. So how this might look like on a little diagram. So this is we'll just say it's a PV diagram, right? Because we've seen a PV diagram before. So a cycle could look something like this, right? You remember this for this one where it went down to here, right? And then from there, so this could be state 1, 2. So remember that polytropic process, we lost some pressure, but we gained some volume. And then the volume stayed constant, but the pressure dropped. But this is like not the piston cylinder sort of arrangement, but you see what I'm saying, right? Essentially, it does this. 3, 4, and then 4 goes back to 1. So essentially this cycle just continues. It is a cycle. I mean, more or less it is a continuous process where you go between these state points every single time. A good example of this is your car. So your car's 4-stroke engine always ends up back at the original point, right? Now obviously it's pistons that are changing their distance, right? So but it always ends up back at its original point. It starts in by bringing in air, right, which is the intake. Then it's the compression phase where it pushes up the cylinder all the way to the top, or the piston all the way to the top. Then the spark plug explodes the gas-air mixture and sends the piston back down. And when the piston reaches all the way back down, the exhaust goes out, and then air comes in, right, using valves. So essentially, whenever the piston gets all the way down to the bottom, it is at the exact same point as it started. So that is what it means by a cycle, is that we are getting to the exact same point in which we started. So from that, uh, basically, this is their other definition. It says, consequently, over the cycle, the system experiences no net changes of state. So that's their their definition of saying nothing changed. If you looked at the course of the cycle, like from stage one to basically the net changes were zero because it all ended up back at the same. So we don't need to think about that anymore, I guess. So right here we have these are two different types of cycles that we are going to be focusing on, and they will be huge in this class and for classes to come. So right here, this is a power cycle. And the reason why it's a power cycle is because work is coming out of the cycle. So this is like, essentially we're taking hot energy and we are sending it through the system and we are getting some sort of work out, right? So this is how power cycles work, like the ones that send power to your house, is that, you remember, I'm sure you guys are probably aware, but when they use a boiler, they heat, or they use nuclear power, whatever it is, to heat up some fluid, water, whatever it might be, to its steam state, its vapor state, and then when it runs through the turbine, spins the blades, and that energy is transferred out, and they send it out to your power grid. Essentially, it's on a generator. So it goes out to your power grid. That's how you get it. So this is a power cycle. This right here is a refrigeration cycle, essentially. So this is refrigeration, which I don't know if that's what they call it. I'm sure that's what it is, though. Yeah, right here. And heat pump. So the difference between this one and the previous one is that this one is taking in work. We have to actually power it. You can see by the direction of this arrow. This one is going out. We are making power. It's going out to the world. In here, we have to put it in. And heat pump cycles and air conditioning cycles work similar to this. We have cold. So essentially, it reverses. You have cold being taken in, and it gets sent out to hot, right? So if you've ever seen the back of your refrigerator, you'll wonder why it's warm back there. That's because that's where the refrigeration cycle is exhausting. So you're essentially removing you're removing air from the refrigerated space, and you're replacing it, more or less, with cold air. So those are the two cycles that we will talk about in this class, and we're going to talk about them generally in this format. You won't see like the actual specifics in 300, but you will see this sort of drawing. Okay? So, cycle energy balance. So really quickly, it says the energy balance for a system undergoing a thermodynamic cycle takes the form of delta E cycle equals Q cycle minus W cycle. And then it says where Q and W cycle represents the net amount of energy transferred by heat and work, respectively, for the cycle. Since the system is returned to its initial state after the cycle, there is no net change in its energy. Makes sense, right? If we start and end up at the same place, nothing has changed in that respect, right? State 1 and the last state are the same. And then it says, therefore, the left side of the equation equals 0, and the equation reduces to that. So work cycle equals Q cycle. All right? So since the change in energy is nothing, right? Because, the net change in energy of the cycle is 0, it becomes this. Q cycle equals W cycle. All right. And then how this question continues to break down is this. So there are two parts of this. There is work cycle. And I'll probably do that somewhere else. But essentially it becomes work cycle is equal to Q in minus Q out. So essentially inside of this Q cycle, there are two terms, right? You have heat leaving and you have heat entering. And so Q cycle essentially just houses that. So there are two things here. It's Q in minus Q out. So work cycle has to be equal to Q in minus Q out, because this makes sense, right? Because remember, we are conserving energy. So energy in the system that is not work, essentially has to be heat transfer, right? Because these are the two methods by which energy is transferred. We've already talked about that in other sections. So if it is not that, it has to be the other one. So that's why work cycle is represented by, if something, let's put it this way, if let's say you have 100 kilojoules going into the system to make power, but only 70 actually turn into power, the rest of it had to leave as heat, right? Because the energy doesn't just get destroyed, right? It's going somewhere and it's leaving through heat transfer. And if you notice, if you ever, I don't know if you guys will ever see a PowerPoint, or not a PowerPoint, a power plant, you will notice that near the turbines, which I know Thermo 2 actually does a power plant tour, so you might actually get to do it at some point, but the turbines are these huge, like, like houses, right? They house them, and it's warm next to them because heat is leaving, right? I mean, there's no way it's going to be perfectly insulated, although I'm sure they try to insulate them as much as possible so heat doesn't just leave in the form of heat rather than work. But you definitely want, you'll definitely notice that it's impossible, right? There will always be heat leaving instead of work. But that equation is the next important thing that we're about to talk about. So let's move down. Power cycles is the first one. So right here, as I said, work cycle is equal to Q in minus Q out. This is for a power cycle. So it says systems undergoing cycles of the type shown in the one up figure 217A, which was the first one we looked at, deliver a net work transfer of energy to their surroundings during each cycle. Any such cycle is called a power cycle. So whenever it delivers work to the surroundings, it's a power cycle. When it takes work from the surroundings, it's a refrigeration. And then it says work cycle equals Q in minus Q out, where Q in represents the heat transfer of energy into the system from the hot body, and Q out represents the heat transfer leaving the system from the cold body, right? And it says from equation 2.41, it is clear, which is this one right here, that Q in must be greater than Q out for a power cycle. It has to be true, right? Because if work is to be positive here, because remember, if work is entering the system, if work is entering the system here, it has to be a positive work, right? Or if it is leaving the system to your surroundings, it has to be a positive work, right? Because if it was coming into the system, it was negative. So if we just put a positive sign here, knowing that a power cycle makes power, we know that this has to be positive. If Q in was less than Q out, this would be a negative quantity, right? So essentially what that means is that this one always has to be bigger than the other one. So the energy supplied by heat transfer to a system undergoing a power cycle is normally derived from the combustion of fuel or a moderated nuclear reaction. Yeah, so that's what I said earlier. It can also be obtained from solar radiation. So this is I've actually seen one of these in Las Vegas, or near Las Vegas, where they heated up all their fluid with just solar panels. And it says the energy Q out is generally discharged to the surrounding atmosphere or a nearby body of water. So that is essentially where the condenser sits, right? The Lake of Egypt power plant, the one near Carbondale, it's a man-made lake, so they could use it as a condenser essentially. So they just have a bunch of water and it's hooked up to that, and that's how they get rid of the heat, the excess heat. Alright, and then it says the performance of a system undergoing a power cycle can be described in terms of the extent to which energy added by heat, Qn, is converted to net work output, W cycle. So the extent of the energy conversion from heat to work is expressed by the following ratio, thermal efficiency. So this is a huge equation for us in all of the thermodynamic classes, so this is something you need to pay attention to. So essentially what this equation is, so real quick, efficiency in our class is this right here. It's eta, right? And so what this eta means is essentially it's an efficiency value. And what that means is that the work of the cycle is being compared to how much possible work we could have had, right? Because remember, possible work is Qn. Would you agree? Possible work is Qn because that's how much we put into the cycle. Whenever we burn, let's say we have a crap load of coal and we burn the shit out of it, and we heat up our water, right? When we do this, the water is going to gain a bunch of energy. Let's just say for this scenario it gains 100, which isn't very. This is just to help me, right? If it gains 100, let's say the water has 100 kilojoules in it right now, and it passes through the turbine, and the turbine makes 80 kilojoules of work, or 80 joules of work, whatever I said, the same units. That means that the efficiency of this is 80%, because we had 100 kilojoules to use, but we only got 80 out of it. So that's why it's being compared here. So W cycle is being compared to QN, because if you have W cycle and QN making the same amount of energy, if all of the energy transferred into heat became work, it is a 100% efficient turbine, or 100% efficient power cycle. So that is and then alternatively, this equation can be written as the follows. Because work cycle, if you recall, is Qin minus Q out, and it can be over Qn, and then it can be written as this. And sometimes it is important to rewrite it as this, because sometimes you aren't given work cycle, you're given Qns and Q outs, so you can rewrite it as the following. So hold on to this one as well, because sometimes it is important to have this in your quiver. All right. And then just so you're aware, obviously the efficiency can never be greater than 100%, because we did not create any new energy. We're just transferring it, right? If your let's put it this way, if you did a thermodynamic process and you got more energy out than what you put in, you have broken all types of laws. So it's not good. And also, if you did that, you should submit a paper like tomorrow. All right, and then moving on to the next one. This is refrigeration and heat pump cycles. So this equation is going to be similar, except that this time we swapped these. Work cycle is equal to Q out minus Q in. All right? And then it says, for cycles of this type, Q in is the energy transferred by heat into the system. So I will draw this in a second. Into the system, undergoing the cycle from the cold body, and Q out is the energy discharged by heat from the system to the hot body. To accomplish these energy transfers requires a network input. So this is a input. This one takes energy to run, work to run. The quantities Q in, Q out, and work cycle are related by the energy balance for which refrigeration and heat pump cycles take the form. So right here is what they look like. So work cycle is equal to Q out minus Q in. So essentially the only difference here is that we've swapped the places of these two. These two have swapped. All right. And then it says, although we have treated them to the same at this point, refrigeration heat pump cycles actually have different objectives, which is true. So obviously you guys know what a refrigerator does, right? Refrigerating essentially just removes warm air from the space and inserts cold air, right? So in your refrigerator, it's essentially recycling. It's taking air out of it that's warm, and it just keeps re-putting in cold air. That's how it stays that same temperature. For a heat pumps actually are the ones that can heat your house or cool your house. So I don't know if anybody knows anyone that has a heat pump, but essentially they work a different way. They work as we'll get to it in a second. We'll talk about refrigeration first, then we'll get to it. It probably makes more sense that way. So this is the next part of the class, is that so refrigeration cycles and heat pump cycles are not looked at in terms of efficiency. So efficiency does not exist for a refrigeration or heat pump cycle. It is what we call a coefficient of performance. So right here, coefficient of performance is how these are related. So coefficient of performance it's essentially the refrigeration and heat pump efficiency. But it isn't an efficiency, so don't get that confused, because coefficients of performance are over 1 or can be over 1. So just hold on to that. So right here, beta is for a refrigeration cycle. So they have beta. It is Qn over work cycle. It essentially is flipped, right? because work cycle used to be at the top. And what this one is basically saying is that the coefficient of performance for a refrigeration cycle is how much heat you removed from the space and compared to how much energy it costs to run it. So if we removed, let's say 200 was removed from the space, and I know you guys might be wondering, well, wait, it says Qn. Well, Qn for refrigerations is different. Essentially, it takes it away. Qn is how much is removed from the refrigerated space, which I will show you on a diagram in just a second. But Qn is removed from the space. I know that it sounds backwards, but it'll make sense once you read it. So Qn is removed from the space. So let's say we removed, I don't know, let's say 250, right? We removed 250 kilojoules from the space, right? And our cycle, let's say, oh man, we read the little we read the little meter, and our cycle cost us, I don't know, 100, right? 100 kilojoules to run. So that means that what? That means that our efficiency, or in this case, coefficient of performance, is equal to 2.5. So as you noticed, this is now above. This is above 1. And your cycles, for most refrigeration cycles, should be above 1. If they are not above 1, or if they're at 1, it means they're trash. It means that you're having to put in more work than the energy you are receiving afterward, or out of the system, which is bad. It's really bad. So generally speaking, most refrigeration cycles lie between coefficient of performance of 2 and 4. So 2 to 4 is where they usually lie. And once again, that equation can be rewritten as the following if you replace Q at a work cycle with this right here. So another little transformation. All right. Now we have the following, which is the heat pump cycle. So really quickly, you'll notice there's a bit of a difference here as well. Obviously, we now have this right here, which is that gamma. Anybody?
I think so, yeah.
Yeah, okay. So we have gamma, or this little weird Y, is now our symbol for coefficient of performance. Again, it is still coefficient of performance, except this one is Q out at the top, not Q in. And the reason why is because in the refrigeration cycle, it's all about what you were trying to do. So real quick, efficiencies in this class and coefficient of performance can be written as like what is the goal over what you had to put in. So it's like goal of the system over input, right? And so if we use that rule and apply it to the refrigeration cycle, what does it say? Essentially, our goal is to remove heat from the system, right? That is what Qn is in a refrigeration cycle. What did we have to put in? The work of the cycle, right? Because you have to run the compressors and all that stuff, right, in your refrigeration cycle. So that is its goal. Our goal was to remove heat over work cycle. Now if we apply that down here, a heat pump's goal is to heat your house, right? We actually want the heat this time. We're not trying to get rid of it. We're not trying to exhaust it. We want that heat. So that's why the equation flips to now Q out is what our goal is. For a heat pump, the goal is the heat out. It's the heat leaving. And obviously the input is still work cycle, right? And so I'm going to draw these in just a second, but I just wanted to show you these. So right here, this is the, once again, the same transformation as before. Just replacing work cycle with some heats. Let me see. All right. So I'm going to go up here really fast because they actually had these drawings. So really quickly, right here is the power cycle, right? So let's talk about that first. As you can see, for this system, we have a power cycle. There is some heat coming into the system right here, right? This right here would be in the form of like a boiler, combustion, like they said, or, some reaction that we're getting some heat in. And then the difference in heat, because obviously there's some heat leaving here, is the work of the cycle, right? The difference in heat here. And so we have the hot reservoir up here and the cold reservoir. Generally, how this works in real life is that the hot reservoir is like a huge, huge boiler where, there's essentially it's just nothing but it's like fire and brimstone and then pipes run through it, which creates heat transfer on the pipes, and the pipes heat up, which heats up the water, right? Or whatever the working fluid is. I always say water, but whatever the working fluid is, it is something. And it heats it up. So that is the hot body is the boiler. The cold body is generally like a man-made lake, a cooling tower. You know those big spires you see at nuclear power plants? Like those huge big circle ones? Those are cooling towers. So cooling towers are the other way of doing this, which does it by like air and humidity. It's a different process, but essentially it's the same. It's a condensing property, right? It's a condensing process. Now, if we take that and look at this one right here, we have a refrigeration cycle or a heat pump cycle. So they're the same cycle, but our goal is different. So don't be confused that the cycle looks the exact same. It's because it is. It's just we want something different out of the cycle. So really quickly, Qin is down here because think of the refrigeration cycle this way. Remember, this is the cold body. So in a refrigeration cycle, what do you think the cold reservoir is? A cold reservoir is where essentially the coldest temperature lies, and the coldest temperature on the refrigeration cycle is going to be what? It's going to be where you are putting your ice cream, right? That's the cold, right? And then the heat entering our cycle is coming from the cold reservoir. And it's coming in from there. So we're removing heat from the ice cream, or whatever, the freezer. We're removing heat from the freezer so it stays cold. And so that's why it's Qin here. So this is the confusing one, but Qin to the cycle is leaving the reservoir. All right. So then we have Qin. The difference between Q out and Qin has to be equal to the work of the cycle because, like I said, there's no other losses taking place that we know of, and there's no losses because it's work or heat, right? Those are the two ways we've described how it can be, how energy can be transferred. And then Q out. This is heat exhausted out of the system to the hot body. And the reason why this is different now, if you switch to a heat pump cycle, is that yes, we actually want this. To heat our house, we want this right here, is the hot fluid. We want the hot exhaust gases to heat our house. In a refrigeration cycle, we want the cold to be removed from the refrigerated space. And how this works in practice is that what ends up happening is that this cycle, depending on what time of year it is, like let's say you're using it to cool your house, there's a reversing valve. And what that does is that it changes the direction of the cycle. So essentially you get either this or this, depending on what type of year it is. You get a different result depending on what how you flip your cycle. Like I said, it's the input, or it's the what we want over the input. So in a refrigeration cycle, we want the heat into the cycle, right? We want to know how much cooling we are doing by pulling it away from the refrigerated space, and we had to put in the work of the cycle. For the heat pump one, we want the heat leaving the system because that we are trying to heat our house, and that is hot, right? It's pretty warm coming out of the cycle. So we want this, and then we obviously had to put in the heat or the work. So we're going to actually do a question really fast because this is all of what we were supposed to do today. So we're actually going to do a question based on this really fast. So I'm going to go find a question about this. Let me see, that was chapter 3, so we're going to move it on back real quick. Alright, right here. We're almost done with this chapter anyway. So let me see, we should find one in here somewhere. Although I wonder if he has an example on here. He might actually have an example to do. I will actually go find that. Let's take a look. Okay. Alright, I think that's, let me see if this is it. No, I don't think this is it. Okay, this is what we're gonna do. We're going to solve a question. We're going to solve one of these questions that you see on your homework. And then we might have time to do a power cycle, refrigeration cycle question. So, because this is a question on your homework, right? You guys agree? If you've looked at it, it looks a lot like this. It has a blank table, and you have to fill out things, right? Hopefully, you guys have looked at it. If you haven't, that'd be real sad. Yep. Okay. So, we're going to do one of these really quickly. And I'm making sure I don't have the same one. I do not. Not using the same question. Okay, cool. So, we're going to do this one right here. So, let me pull open Paint 3D. The greatest program ever. 5,000. Give me some room to work here. Alright. So, I'm going to snipping tool that table and put it in here as well, because that'll make things easier for me. Alright. Great title. Alright. So I'll have to go back and forth and read this. Alright, so we're going to put it right here. So, these are our values right here. So essentially how this one works out is, let me read it. So it says each line of the following table gives data for a process of a closed system. Each entry has the same energy units. So it could be kilojoules, whatever it is, but it doesn't matter. You just need these numbers. Determine the missing entries. Okay? So, we're going to do this question really fast. So essentially what we're going to do is we have to fill in these missing numbers, right? Fill them in. And so I'm going to make our own table here. I could have just made that picture bigger, I guess, and wrote them in. That would have been smart. So let's actually do that instead. And I'll just write them in as we go. Okay. So now we have a bigger picture here that I can put in the numbers in between. Alright, so let's start with process A, just to give you guys a little input of like how we should do this. Let's start with process A. So process A, remember, you have to rewrite this equation. So remember, this is the equation. I'll actually use the text for this one because it probably makes more sense. So let's start with process A. A. So remember, delta E, so I don't really have a delta, but I wish I knew the triangle button for this. 2D shapes. Let's do that, and I'll save this. So, alright, so delta, and then let's do this. So let me do that. Delta E is equal to, right, Q minus W, right? You remember this equation? Hopefully you do. This right here is that base equation. And now inside of delta E, there's obviously E2 minus E1, right? So I will write that first. E2 minus E1, right? Is equal to Q minus W. So what we are trying to figure out is, using these numbers that we already have, how do we get these other two numbers? So does anybody want to take a guess as to how we do it using these equations? These aren't very hard, by the way. Like, these are pretty straightforward questions. So I hope there are some answers.
Basic algebra process, right?
Yeah, basic algebra process. So since it's a basic algebra process and your mic is working, walk us through the first one. So how would you do this?
I would fill in the information that we were given. E2 is positive 50, E1 is unknown, Q is unknown, and W is negative 20.
All right. So that is what he has said. So essentially we have 50 minus E1 is equal to Q minus, and then inside a quantity, because it's already a negative, we have to put that there, right? So this is what we have going so far. Now, what else do we know? There's something in here that I didn't mention, but right here it says delta E is 70, right? So that means the change in energy is 70. So what does that mean for this question? What is E1 then?
Negative 20.
Is that negative 20? So what he's saying is right here, let me replace this with negative 20. So what he said was that because delta E is 70, we have 50 minus, and then obviously it has to change to a plus to get us to 70, right? So does that make sense for everybody? I think it makes sense for me. Right? So that means now we have 70 is equal to Q minus the work, right? So now from here, very simple process. We can then maneuver around and get, so now we have 70 is equal to Q, essentially plus 20, right? That makes sense? Because minus a minus has to equal plus, and then you subtract it over, so heat has to be equal to what?
50.
50. So, if that makes sense, hopefully it does, equal to 50. So, I'm going to go ahead and write it in there. We're probably going to only do one more of these, because, I mean, honestly, I think you guys can probably do this, right? I don't think it's super difficult for you. But I'm going to do probably one or two more of these, and then I'm going to go do a question on the refrigeration cycles. Negative 20. Ooh. Let's do that. Negative 20. Alright. So that's the first one. Now, let's do the next one. So I'm going to go ahead and... Oh, that's right. I got to put a delta out here. So then we have... So let's do this. Delta E is then equal to, once again, Q minus W. I like to rewrite it out because I'm a psychopath. So let's do E2 minus E1 again is equal to Q minus W. I'm trying to get you in good habits. Now let's fill in our information on the third one. So we have, this time, heat transfer E1, E2. All right? So let's write this out. So E1, or E2 is 50 minus our E1 value, which is 20. So 50 minus 20 is then equal to a Q value of 50 minus, let's just say work, right? So that is our, so far our equation. Now we just need to fill in the things that we don't know on the table. So what we don't know work. We do not know delta E. So delta E is probably pretty straightforward for you guys because delta E is just the difference between these two. So E2 minus E1, which is 30, correct? So I will go ahead and write that. That really sucks. That's one thing I do not like about Paint, is that it does that a lot because I'm really bad at this. Should have watched me do this in what is it, 309 for like, you know, every lecture. Alright, so then E2 minus E1 equals Q minus W. And then we got, what did I say it was? It was 50 minus 20 And so, with that knowledge, we now know that we can make a new box, so I don't do that again. And we could say delta E, so E2 minus E1 is equal to 30, which means we have delta E. That one's pretty straightforward. And then we have to find the last one. So now that we know that this is 30, so it's 30 is equal to 50 minus work. So if we move work to the other side and you subtract over 30, you get 20, right? Anybody figure that? I mean, I'm sure you guys are already well ahead of this, but this right here is it's questions on your homework and probably maybe one on your exam, so probably helpful for you. Move that over, yep, and then it's 50 minus 30, which equals 20. So, and then you fill out the table. So this is what you'll be doing on your homework, hopefully. If you guys haven't already done it, maybe you have. Haven't even looked at it, probably. And 30. So this is what you do for that. So this kind of question, very straightforward. You could probably knock this out in like 5 minutes or less, right? Not very difficult. Now let's move on to the next one. The next one, which I will pull up another question for you guys, is I'm going to find a power cycle one or something like that, which I have to go and look for. Okay, here it is. So right here, let's try this one right here. So let's do for a power cycle, the heat transfers, so we're going to do this right here. So power cycles, I'm going to pull up Paint and I'm going to minimize it so I can write this out. But first, I'm going to actually delete all this stuff off the screen because we don't need it anymore. Alright. Don't need it anymore. So, what it says is, it says for a power cycle operating in that figure. So that figure is the one that we saw in the chapter, the one that I explained, the ins and outs of the heat transfers. That's where that figure is. So it's 217A. And so, I gotta get the text tool. Text. So, right here, it says for a power cycle, so I'm going to write our knowns and unknowns up here. So it says for a power cycle operating as that figure, the heat transfers are Q in as 75 kilojoules and Q out as 50 kilojoules. Determine the net work in kilojoules and the thermal efficiency. So Q in is equal to 75 kJ. Q out is equal to 50 kJ. Once again, another basic math process. We need to find what the work is and what the in. I'm just going to put it as lowercase n, but it's thermal efficiency. It's that eta value, right? So, so that is our question right there. Is what is Q? Knowing these two, what are the other ones? And so we can pretty much do that, right? So if you guys recall, the equation is work for a power cycle is Q in minus Q out, right? And so if you plug in our numbers, you get 75 minus 50, which is therefore equal to 25. And so we now know that the net work is 25, or the work of the cycle is 25. Is everybody following? I'm probably putting you all to sleep, but this is important, I promise you. First exam is really important to do well on. So 25 is the work of the cycle, and then from there you have to do eta. So the eta equation, remember, is the thermal efficiency of the cycle, and it is what you want out of the cycle divided by what you had to put in. So can somebody in here, let's call on, this is where I find out where someone's not actually here the whole time. Let's go with Luke. Are you here? And if he's not here, we're going to Joseph. Looks like not here. Both of them not here. Oh, okay, Joseph is here. Yeah, he's here. So tell me, in the efficiency equation for a power cycle, what are we trying to get out of the cycle? What should be on the top of this dividing part? So what is the efficiency, essentially? What do we want out of a power cycle? Work, yes. So we want the work cycle, right? Or essentially in this respect, the work, right? The work value. So work cycle. And what did we have to put in for this cycle to run? Remember, think of it in terms of your car. Think of it in terms of like boilers. What did we have to put in to get that to work? Energy. What specific energy though? Is it heat in or is it heat out? Heat in, correct. So that is our eta cycle. And so using this, oh, you typed in the wrong chat. That's all right. Just make sure it's wait. Which one were you in? Oh, you were in the 411 one. Oh yeah. Sorry about that. So that means right here we have a value of 25 divided by what is it? 75. Right? Is that correct? Yeah, that looks good. So you have 25 divided by 75, which everybody can probably tell me that that is a third, right? So this is 33.33%, right? So power cycles, that's actually like in the range of typical for thermal efficiencies of like big Rankine cycles, which are like the ones that get you power. That's pretty typical. Anywhere between like, you know, I would say high 20s to like high 40s or low 40s. I know some cycles, it always comes across in like science magazines and stuff where there's apparently some cycles that have gotten into like the 70s, which is ridiculous. Like, that's amazing. But this is kind of what it is. So essentially what this means is, guys, is that when a power cycle is making your power, they are getting only 33% of the total energy to change into work, is what that means. So we only get a third of the energy that we put in out of this cycle right here. It's not good, is it? But that's why you guys are learning, so you guys can change this in the future and make it better. Alright, so that was this a power cycle. I'm not going to do a refrigeration cycle because we're out of time, but essentially you would solve it the exact same way. They would give you some things, like here, I'll even show you. So it says a refrigeration cycle operating in that figure, so the previous one has a Q out of 1,000 BTUs and a work cycle of 300. Determine the other ones, right? But this time you have to do coefficient of performance, not efficiency. So as long as you follow the equations and you know what each thing's equal to, like work cycle is Q out minus Q in, you can solve these pretty simply, right? And I think there are questions like this on your homework as well. All right, so before I'm going to go ahead and stop streaming and then, or stop recording.